Welcome everyone. Welcome to lecture 6. So let us continue our discussion of symmetry elements and symmetry operations. In this set, we have last symmetry element and symmetry operation, which is called as improper axis, and corresponding operation is called as improper rotation. Improper, uh, rotation. So this particular symmetry element and symmetry operation is a combination of two symmetry elements and operations corresponding this thing. So first is proper rotation through proper axis. We have already seen what proper axis is. And the second part is reflection perpendicular to proper axis. So reflection via a plane which is perpendicular to proper axis of rotation. This also we know that this is called as Cn, this is called as sigma, and improper axis or improper rotation is denoted by Sn. Okay, so we have Sn. Now this Sn is a combination, as I said, it's a combination of Cn and sigma, and it does not really matter in which order you apply individual operations here. So you can apply Cn first. So in this case, this will be the first operation and this will be the second operation, or you can apply sigma as first operation and Cn as second operation. Okay, so let us see with an example how this particular improper axis can be understood. So let us look at an example of staggered ethane. Staggered ethane. How do you draw this molecule? So we have C, C, H, 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 right? You must have seen this drawing earlier, but in symmetry class, you will never draw a molecule like this, okay? Because it does not tell you where the orientation of each hydrogen is. So what is the next best thing which you can do is to draw it in which also does not give you very great details, but it is still better. So this one would be actually the eclipsed ethane. So if you want to draw the staggered one, you can draw like this: H, 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 and then right. So this will be the staggered ethane. But to carry out any sort of symmetry operation in this will be really difficult. So the easiest way is you must have learned this Newman projections. So how do you draw? So this is one set of protons. This is the other set of protons, right? So you have H, now let me also write down the numbers 1, 2, 3 and 4, 5, 6. Okay, so now let's see how we do this operation. So as I said, we can do C6 first. So okay, so what kind of Sn we are looking for here? Okay, so we are looking for S6 in this case. Why S6? Because this will be 2 pi by 6 operation. What is 2 pi by 6? What will be the angle? So this will be 360 by 6, which will be 60 degrees of rotation. So where is the 60-degree angle over here? So let's see. This particular angle, this whole angle is 120 degree between two hydrogens on one carbon. But if you look at this dihedral angle over here, this dihedral angle is 60 degree. So we'll be doing this rotation, 60-degree rotation. So we can also see if there is any S3 axis present or not, but let's go ahead with S6 and see this example. Okay. All right. So let's do. So S6 should be materialized by either doing C6 first or sigma first, or in vice versa, because both these operators commute with each other. We know what the meaning of commutation is, right? We have seen this in the first class. So these two operators commute. We can test it out, but let's first do it. Okay, let's first do the C6 one. So we are doing this one first. So C6, that is this one first, right? Okay, let's do both actually. It'll be easier. So in this case, this is the first one. So we are doing both ways. Okay. So now if you do C6 operation first, this C6 operation means that H1 will move to this part, H3 will move to this part, H2 will move by 60 degrees, right? Every proton will move by 60 degrees. So how does it look? So that means instead of a inverted Y, we have a upright Y, right? And then instead of upright Y at the back, we have inverted Y at the back now. So now let us also write down the numbers. So this 60-degree anti-clockwise rotation means H1 comes here. This will be 2. This will be 3. Now H4 comes this side. So this will be your 4. Then 5 goes there. So we have 5 over here. So we have to be very careful when we are writing these numbers, because otherwise it will mess up everything. 6, right? So this looks like right. Now you can see that if we denote this as molecule number 1 and this one as molecular number 2, so 1 and 2 are not in equivalent configurations, right? You can see that the configuration of this is not equivalent to this. So we can say that C6 does not exist in this one. So C6 does not exist. So we can do the operation, but it may or may not result in equivalent configuration. If it results in equivalent configuration, we say that it does exist. The corresponding symmetry element does exist, but in this particular case, C6 does not exist, right? Now let's do sigma. Okay. So where is the, so sigma has to be now perpendicular to this C6 axis. So where is our C6 axis? C6 axis is actually passing through the two carbons. Okay, so I'm drawing it perpendicular to the plane of the board. So I'm drawing it like a circle with a dot inside. So this is my C6 axis. So the plane, this particular plane now has to be perpendicular to the C6 axis, which means that the sigma is the plane of the board. So that means whatever is in the forward will go in the backward, and whatever is in the backward will come forward, right? So that means this H1, H2, H3 will go to the back upon this reflection, and H4, 5, 6 will come forward. So that would mean that you have, draw it like this. So this will become your, okay, let's write the hydrogen first and then we will write the numbers in red. So H1, 2, 3, and then this is 5, 4, 6, right? So now you can see, let's say if this is our third, so first and third are equivalent, because you can see that this is inverted y, this is inverted y over here, and then there's the upright y at the back, upright y at the back. So you can clearly see that the first and third orientations or configurations are equivalent. So we can safely say that S6 exists, right? So S6, which is a multiple of product of two symmetry operations. The first is C6 and the second is sigma. So we have seen that it does exist. Now let us also look at the commutation part, whether it does it really matter if we are doing C6 first followed by sigma, or we can do sigma first followed by C6. Okay, let's do sigma first now. So if we do sigma first now, again this inverted y goes back, so the front carbon goes to the back and the back carbon comes to the front. So that means it will be something like this, and this is the back carbon which is now in the front. Hydrogen, hydrogen, write down all of these hydrogens explicitly, and then the numberings remain 1, 2, 3. Did I mess up the numbering? 1, yeah, 1. This should be 2 actually, right? And this should be 3. So accordingly this should be 2, this should be 3. Okay, and then the 4, 5, 6, 4, 5, 6, yeah, this is correct. Okay, so 1, 2, 3. So that's why I said the numbering has to be right. And this is my 4, 5, and 6. Okay, so now again you can see that, let's say this is our fourth configuration. So first and fourth are not equivalent, so we can say that sigma does not exist. Okay, now if we do C6 on this, C6 means again it is a rotation by 60 degrees anti-clockwise. Okay, so that would mean now what will be the numbering? So 1 comes over here, and then 2 comes over here, 3 comes over here, and this will be 4, this will be 5, this will be 6. And now if we call it as fifth, you can easily see that the first, third, and fifth are equivalent. So because first and fifth are equivalent, we can say that S6 exists. So this is verified again. And because third and fifth are equivalent, we can say that C6 sigma or sigma C6 both are equivalent. So that means the two operators are commuting, right? So okay, so we have now verified that S6 is present in this particular molecule, but we have seen that C6 or sigma may not, it does not exist independently in this case, right? There is no independent sigma independently or C6, right? Okay, so now let us look at how many operations number of operations generated by Sn. So in general, okay. So let's take the general example before we actually look at the operations. So if we do Sn, so Sn will be Cn sigma, right? If we do Sn to the power n, it will be Scn to the power n sigma to the power n, which is nothing but Cnn. We have seen that Cnn is E and sigma to the power n is E. Only in the case of n is E1, right? Okay, so let us first consider the case of n, E1n. So this will be equal to E, right? This is easier to follow. If it is not E1, then it will lead to sigma, right? Cn to the n will remain E irrespective of even or odd, but sigma n will give rise to sigma if n is odd. Okay. So now let's say Sn to the power n plus 1. What happens there? So that would be Sn to the power n Sn. That means since this was E, so this was E, so we can say this is Sn. Similarly, if we have Sn to the power n plus 2, power means how many times a particular operation is done. This can be written as Sn Sn2. So you can say, so now there is a trend, right? You can see that if you are increasing this power one by one, so you are getting the same operations back. So that means after Sn to the power n, it starts to repeat. So that means that it does not generate more than n operations. So we can safely say then for E1 n, Sn generates n operations. We will see for odd case also, but let's this is for even n. Okay, n operations. Okay, so now let us see the case of S6. So we had S6 equal to C6 into sigma, right? So this is S6 to the power 1. So this is an independent operation. Now let's say S6 to the power 2. This can be written as C6 to the power 2 sigma to the power 2, right? Now this can be written as C3. C6 done twice is nothing but C3. Sigma done twice is nothing but E. So you have C3, right? So this operation is different from this operation. Now S6 to the power 3, this will be equal to C6 to the power 3 sigma to the power 3. That means now this is C6 done 3 times is nothing but actually C2, and sigma done thrice will be sigma. So this is again a independent operation. Now S6 to the power 4 will be C6 to the power 4 sigma to the power 4, which is C3 square E. So this is C3 square. So C3 done twice is S6 done 4 times. Okay. S6 to the power 5 will be equal to C6 to the power 5 sigma to the power 5, which will be C6 to the power 5 sigma, right? So again, this is not come so far. So it's a non-redundant operation. S6 to the power 6 is nothing but C6 to the power 6 sigma to the power 6, and both are equal to E. So again, this is also a non-redundant operation. Okay, so this is a case for uh, even n. When n is even, how many operations it will generate. So now we have seen that uh, for even n, we can also say that if Cn and sigma exist independently, Sn must exist, right? This we have seen from this one over here. So if you have uh, C6 and sigma present independently, the S6 will present because it's a product of the two. If Cn and sigma does not exist, Sn may or may not exist. So we have to actually do it and test. There is no rule which says that it must exist or must not exist. If Cn and sigma does not exist, we have seen this example. In this particular case, C6 or sigma, neither of those two were present, but still S6 was present, right? So we can safely say that if they do not exist, Sn may or may not exist. So you actually have to test it out whether it is present or not by actually doing the operations. But if they exist independently, you can safely say that it must Sn must exist. Okay. So one more interesting thing, if you notice over here that when S6 was present, three operations were present. So if you notice over here, there is C3, there is C3 square, there is E, right? So when S6 is present, a set of operations C3, C3 square, E are present. Why am I interested in this? Because C3, C3 square, and E can also be written as C3 cube, right? So this is equivalent to E. So these three operations indicate that, implies that C3 exists independently, right? So when S6 was present, C3 was present independently, irrespective of C6 and sigma. So that means we can generalize this for even n. If Sn is present, Cn by 2 must be present. Okay, so we will see these kind of corollaries a lot. So this is an important one. So you should know, if Sn is present, Cn by 2 must be present. Okay. Vice versa may not be true. Huh? So if C3 is present, it is not necessary that S6 will always be present, but uh, vice versa may not be true. Okay. Now let us look at the case for odd n. So for odd n, what happens? So let us do the same exercise that we did for Sn, but in this case now we have Sn even. So if we have Sn, what do we have? Cn sigma, right? Sn1. Now it's easier actually if we take an example. So let's take let us take n equal to 5. We can also take 3, but let's take 5 just to make it more clear. So let's move to next page and see. So S5 is equal to C5 sigma. S5 done twice is equal to C5 done twice sigma done twice, which is nothing but C5 done twice because sigma square is E. Now S5 done thrice is equal to C5 thrice, and now I'm shortcutting it to sigma. Sigma done thrice is equal to sigma. S5 done 4 times is equal to C5 done 4 times. Now sigma to the power 4 is equal to E, so I'm not counting that, right? S5 to the power 5 is C5 to the power 5 and sigma to the power 5, which is, this will be E and this will remain as sigma, right? So we are generating, all of these operations are non-redundant operations so far. So we have reached S5 to the power 5. So that means now if we should see whether we start to get this operation back or we are getting some different operation. So what I mean is, in case of Sn plus 1, when we tested here, so we were getting Sn back, right? Sn plus 1. So in case of n plus 2, we were getting Sn2 back. So let's see what happens here. So S5 to the power 6, do we get Sn back or not? So this will be C5 to the power 6 sigma to the power 6, which is C5 done once and sigma. So this is not equal to S5. So that means we need to keep going, and because we are still getting non-redundant operations. So let's keep on going unless we actually get the same operations back. So when the redundancy starts, we need to stop. Unless we get non-redundant operations, so we need to keep on going. Now C5 to the power 7 sigma to the power 7. So this means C5 done twice and sigma, right? So again, this is a non-redundant operation because this earlier was C5 square. Now we have C5 square and sigma. Now S5 done 8 times is C5 done 3 times, and that's all, right? So now again, this is a non-redundant operation. Now let's continue. S5 to the power 9. So we have C5 4 and sigma. So I'm shortcutting this. You can explicitly do it and see. So what you have to make sure is that whenever you are hitting, this is equal to E. Whenever you are hitting sigma square or even powers, this is equal to E. So I'm using this, okay, to simplify this. Okay. Now S5 to the power 10, we are getting C5 to the power 10, that means, and sigma to the power 10, that means again E, right? So again, we have got a non-redundant operation. So let's see what happens next. 11, C5 5, C5 5, C5 1, sigma 11, right? So this is E, E. Now we have C5 and sigma. Now if you notice that this is a redundant operation, right? C5 sigma, C5 sigma. So now if you go with S512, you will notice that this will be equal to S52. So you can do this yourself. So you will get this thing back over here. Right? Okay. So that means for odd n, Sn generates two n operations. Right? Instead of n operations, so we are getting 2n non-redundant operations. 2n plus 1 was same as S1. 2n plus 2 is same as n equal to 2, and so on. Okay. All right. So this is simple. And one more point here is that Sn for Sn to exist, Cn and sigma must exist independently. So this is for odd n. Okay. So for odd n, Sn to exist, Cn and sigma must exist independently. Okay. So that finishes the discussion on symmetry elements and symmetry operations, and we will take one more class to actually see how to locate all these symmetry operations and symmetry elements, and then find out corresponding symmetry operations, and then we will move to next topic, which is product of symmetry operations. So that's all for today. Next class we will look at how to implement these symmetry elements in different molecules and find out non-redundant operations. Okay.